we'd like to introduce the conserved quantities in the three-body problems. We call the Jacobi integrals. So we start with the basic equations of the x2 dot minus 2 omega y dot equal round u round x. This is equation 1. And the y2 dot plus 2 omega x dot equal round u round y. This is the equation 2. And the g2 dot equal round u round g. This is equation 3. We have these three equations. We consider the first equation times x dot plus second equation times y dot plus third equation times z dot. The first equation becomes x dot x2 dot minus 2 omega x dot y dot plus from the second equation y dot y2 dot plus 2 omega x dot y dot from the third equation z dot z2 dot equal right hand side x dot round u round x plus y dot round u round y plus z dot round u round z. And if you look at the right hand side, second term and the fourth term is cancelled out because these terms comes from the Coriolis force. This indicates the Coriolis force doesn't work. So from the rest of the terms we could combine inside of the derivative 1 over 2 x dot square plus y dot square plus g dot squares equal du dt. So dx dot is a dx dt, y dot is a dy dt, dg dt. So we could combine these three terms into the single terms. Then from these equations you can just move to the right hand side time to the left hand side and combine 1 over 2 x dot square plus y dot square plus g dot square minus u equals 0. So these quantities have to be the constant. So 1 over 2 x dot square plus y dot square plus g dot square minus u is constant. So if you name the c. So instead of this c, we consider the 2u minus x dot square plus y dot square plus g dot square. It becomes minus 2c. And we name this is c sub j. This is Jacobi integrals. And go back to these questions. Jacobi integrals is expressed these quantities. C sub j is a Jacobi integral. This is conserved quantities. Then when the C sub j is some quantity, we'd like to consider the motion of the object with mass of m. When the C sub j is a 3.9, then what's happened to the motion of the object with a mass of m? This is the position of the m sub 1 and m sub 2 is located here. The v square, and definition of the v square is expressed this one. C sub j is expressed 2u minus b squared. So b squared is expressed 2u minus c sub j. So as a 2u, this corresponds to the 2u. And the first terms of the 2u, so like omega square, x square plus y square. This terms becomes really large values at the x and the y becomes really huge values. So this corresponds to these regions. X and y is a really huge values. Then the first term of the 2u, these terms becomes really big numbers. In these regions, actually b square becomes positive value. So this means particles is allowed to move in these regions. And if you consider the second term of the 2u, so these terms, so 2gm sub 1 over r sub 1 plus gm sub 2 over r sub 2. This becomes really large values. At r sub 1 is much smaller than 1, or r sub 2 is much smaller than 1. So if you go back to these regions, this region is r sub 1 is much smaller than 1. So this means v squares is positive. This is the allowed regions for the particle with mass of m can move. Also in these regions, r sub 2 is much smaller than 1. So v squares is positive. Also the particle can move around these regions. So our particles can rotate around either object with mass of m sub 1. So particle can rotate around m sub 1, or particle can rotate around the object with mass of the m sub 2. Or particle can rotate in the far place from the both of the object. Like a particle can rotate far place from the both of the object. But particle cannot get into these regions, these blue regions, because in these regions b squares becomes negative. B square cannot become the negative quantities. We call that this is excluded regions. Because a particle with mass of m is not allowed to enter in these regions. This particle is rotated around m sub 1. They cannot move to the orbit around m sub 2 because they have to pass through these regions. It's not allowed. Okay. Then we'd like to move next case. In the case of the C sub j is a 3.7. In this case, two regions share the space. These regions share the space. Particle can change the location near the m sub 1 to the regions of the m sub 2. So freely can move, passing through these two regions, because the two regions share the space. So particle originally rotating object m sub 1 is possible to orbit around m sub 2 eventually in this case. Okay, this is the end of this session.